Okay. Thank you to the organizers for having me at this fascinating conference, which, to be honest, is a little bit outside of the sorts of things that I have, traditionally been interested in. But it does seem to intersect some of the topics that have to do with classical simulation that I'll tell you about today, and I'm fascinated to discuss with you and learn more about those connections in the coming days. So I'm going to speak about some joint works with these authors, and of course this builds on a body of work by other people as well, and I'll try to mention some of those references as we go along. So, as I said, we're going to be interested in classical simulation of quantum circuits, and there are, yes. Oh, hold it closer like that. Yeah, okay. So we're going to be interested in classical simulation of quantum circuits. And there's various ways that you can classically simulate a quantum circuit. And for the purpose of this talk, we're only going to be interested in two. And if you are for some reason interested in some different type of classical simulation, come talk to me afterwards and we can discuss how these methods might be applied there. But for this talk, we're going to be interested in sampling from the output distribution of a quantum circuit, so the full m-bit output distribution. And we're going to be considering either exact simulation, where you sample a bit string from that distribution exactly, or approximate simulation, where you're given some, epsilon, like maybe epsilon is inverse polynomial in the number to its n, and you want to sample a bit string from a distribution that is epsilon close in total variation distance to the output distribution. Okay, so these are the sorts of sampling techniques, and we'll call them exact simulation and approximate simulation. Okay, so, and we're not just going to be considering simulation of general circuits. We are interested in simulation methods that that move outward from the Gosset simulation of Clifford circuits, and we're going to be interested in the question of what is the classical simulation cost of a circuit with m t-gates as a function of m. So when m is 0, it should be polynomial in m due to the Gosset theorem, and then we were asking what is the scaling with m. And the way that these simulation methods, well, one way that they can be made to work is using this gadget that implements a t-gate using Clifford operations, classical control, and single qubit magic state, which is a non-stabilizer state that is consumed by this gadget to implement the t-gate. And this notation of A for the magic state I'm going to use throughout the talk. So just remember that A is a magic state wherever you see it. So using this gadget, you can take any Clifford plus D circuit which has m t-gates and replace them all with this gadget, and then you get an adaptive Clifford circuit where the input state has m magic states at the input and everything else is Clifford, or adaptive Clifford. So this is what you get. And how do you simulate this circuit, or what is one way to simulate this circuit as kind of pioneered by Robbie, Smith, and Smolin in 2015. So the first step is to approximate the input state, which is magic state in tensor product with all zeros. So the first step is to approximate that as a superposition of some number chi, which hopefully is much less than 2 to the n, stabilizer states. So that's this this right here. Can you see the laser pointer at the back? Yeah. Okay. So this is you approximate this magic state as a superposition of chi stabilizer states. Then once you have this, the Clifford operation acts linearly on the terms in the superposition. So we can use Gauss and oh, I think this is out of batteries. Oh, excuse me. Okay. Okay, thank you. So then you can apply the Clifford operation, which acts linearly on all the terms in the superposition. And then the slightly tricky bit is to simulate the final measurement. So we'll talk about that in a second. Right, so what is the cost of these methods? So the runtime for, if you approximate the magic state as a superposition of chi stabilizer states, well, you have to store those chi stabilizer states. So that will take a linear runtime in chi up to polynomial factors that we don't care about. And then applying this Clifford operation, well, you apply it to each term individually, and again, that's linear in chi. And then this simulating the final measurement is tricky because what you have is you have this output state, which you've updated the input state according to Clift operation. So everybody's a Clift or a stabilizer state. You have chi of them. How do you sample from the n-bit output distribution? Well, one standard way to do that would be to compute the marginal distribution of the first bit, sample that bit, then compute the conditional distribution of the second bit conditioned on your sample from the first bit, and so on. Go bit by bit sampling. And if you think about what kind of data do you need to compute to make that work, well, it's all these marginal distributions. And each of those marginal distributions looks like this for some string x. All the conditional distributions can be expressed as ratios of these things. And unfortunately, this expression is quadratic in the state, right? So that means that if you were to just compute this explicitly by expanding it psi out using the sum, it would have a quadratic cost in terms of chi, because you would get chi squared cross terms in the sum. So that was kind of the original scaling, but then in our paper from 2016, we showed that at least for the approximate simulation task, where you aim to approximately sample from the output distribution, this could be improved to chi, linear and chi. And that was based on what we call the norm estimation algorithm, which simulates the measurement via a sequence of like randomized projections onto random stabilizer states. And I'm not going to go into the details of that because to some degree it is superseded by a new algorithm or a new way of simulating this measurement that we call the gate-by-gate algorithm that was in a paper with Sergey and with my student Calvin Liu from last year. And this algorithm is capable of both exact and approximate simulation and will give you a linear scaling in time. So because this is such a simple algorithm, I want to just show it to you on the next slide, but it's okay if you don't process it in real time, and you can ask me about it later. So here's the algorithm. By the way, this algorithm works for not just Clifford plus T circuits. It's like a general reduction from, if your goal is to sample a bit string, then you can use this algorithm. And what you're asked to do in the course of the algorithm is compute output probabilities of subcircuits of the circuit that you started with. So here, there's m steps. M is the number of gates in the circuit. And in each step, you have to compute 4 output probabilities. But these are not marginals. They're n-bit output probabilities. And each one of them has to do with a subcircuit consisting of the first t gates. T goes from 1 to m. So if you have a decomposition of this, state prepared by the first t gates as a superposition of chi stabilizer states, well, you can just take the inner product with x and sum those chi terms, and that's how you can see that this is linear in chi. Okay? Right. Okay, so this is sort of some generalities about these methods. And, let's talk a little bit more about the cost. We said everything's linear in chi, but we didn't really say what chi is. Like when I say approximate input magic state, I've been deliberately vague here, and now I want to say a little bit more about that. So what kind of approximation is needed, and how big is chi? Those are the kind of questions that we need to answer. So that leads us to the notion of stabilizer decompositions and these quantities called stabilizer rank, which was introduced by Bradley, Smith, and Smolin, which is the minimum R for which the state of interest can be expanded as a superposition of R stabilizer states. And similarly, one can define the approximate stabilizer rank where we allow ourselves a little delta error in the approximation. Okay. And okay, so I have a little remark on stabilizer. These decompositions into stabilizer states, it's you shouldn't think about it as like you're decomposing into some, well, it's certainly not that you're decomposing into an orthogonal basis, like a Fourier decomposition. It's not like that. Because you should think of stabilizer states as some kind of generalization of quadratic Boolean functions. Because well, any stabilizer state can be parameterized by a quadratic function, a linear function, and an affine subspace. And so if we take, there's a subset of real equatorial stabilizer states that corresponds, is one-to-one correspondence with quadratic Boolean functions. And so if you think in your mind about stabilizer states as being like some kind of generalization of quadratic Boolean functions, then it's natural to think about, the decomposition of a state into the overcomplete basis of stabilizer states is similar to the idea of decomposing a Boolean function into quadratic Boolean functions, which is what's studied in this field of quadratic Fourier analysis. And the complication arises because of this overcompleteness, that you might be interested in very concise decompositions like we are with low rank, but there's just so many, because it's overcomplete, there's lots of linear dependencies and many different ways of expanding a given state. And that's the challenge. Okay, so just getting back to the scaling that we were talking about. So the classical simulation cost for exact simulation is linear in the exact stabilizer rank, and the classical simulation cost of approximate simulation is linear in the approximate stabilizer rank. And oh yeah, and then let me make just a few remarks, and then we have to get into what are these quantities, right? I mean, that's once we have a simulation method and the cost is linear in these quantities, these that we've defined, we have to understand how they behave and what they are. But let me just make a couple of remarks. These techniques can be extended to circuits with that aren't Clifford plus T, and they don't have to be based on gadgetization, like I mentioned. Yeah, so immediately you can say that, for example, this exact stabilizer rank has to increase exponentially with m, because if it didn't, then you could compute output probabilities of quantum circuits, which are sharply hard to compute in polynomial time, for example. But the problem is that mathematically it's hard to show good lower bounds, and the best unconditional lower bound was improved this year. The best one is a lower bound that is m squared on the approximate stabilizer rank of m magic states, and that's a lower bound on the approximate stabilizer rank is a stronger thing than the lower bound on the exact stabilizer rank. So this is an impressive result, but still far from the scaling that we expect, which should be exponential enough. Okay, so in the rest of this talk, I want to tell you about the best upper bounds that we know on the stabilizer rank and related quantities that lead to the best known algorithms for simulating Clifford plus T circuits. Okay. So first, let's talk about approximate stabilizer rank. The actual upper bound here is very simple. Okay, so first of all, maybe I shouldn't have put delta here. I mean, the delta is important because we're talking about approximate stabilizer rank, but in your mind, maybe just think of delta as being like a small constant or something, just to simplify this formula in your mind. And then if the scaling here is actually cosine squared pi over 8 to the minus m, okay? Or it can also be expressed as 2 to the alpha m, where alpha is 0.228. And this is the best known upper bound, and how do you get it? It's very simple. This magic state is Clifford equivalent to a uniform superposition of 0 and plus, which are non-orthogonal single qubit stabilizer states. And if we take m copies of this single qubit state, we get a uniform superposition of all the 2 to the m states in this non-orthogonal basis. But because these are non-orthogonal, maybe we can throw some of the terms away in the superposition and still get a good approximation. And that's what we do. So we just throw away, we just take, instead of the full sum over 2 to the m terms here, we restrict the sum to a linear subspace of f2 to the m. And the size of the number of strings in that subspace is asymptotically captured by this. And we know that gives you a delta approximation to the state. So that's how you get the best upper bound that we know. And I should mention that the scaling with delta, the 1 over delta squared, is not optimal. It was improved to, I think, inverse linear in delta by Sen, Regula, Ouyang, and Campbell. It's natural to ask whether or not the scaling with m is optimal. Obviously, we can't answer that question in the absence of lower bounds. One can show it's optimal if you restrict to certain types of stabilizer decompositions. But we also attempted to provide some further evidence for this conjecture by studying other related quantities like the stabilizer fidelity that we heard about yesterday and the stabilizer extent. So now I'm going to tell you about that story. Okay, so what is the stabilizer extent? The stabilizer extent is, if we have a state psi and we expand it
as a superposition of stabilizer states with some coefficients, the stabilizer extent is the minimum one norm squared of these coefficients. Okay, so for any stabilizer state, we only need one term, and the coefficient would be 1. So any stabilizer state has extent 1. But this one norm is, it somehow captures how far you are from the stabilizer state. And in fact, it upper bounds the approximate stabilizer rank in this way. And the reason it upper bounds the approximate stabilizer rank is because if you give me a decomposition with low one norm, then I can convert it to a decomposition with low rank and with only making a small error. And the way that you do that is you sample these terms in this sum with probabilities proportional to the magnitude of the coefficients, and you construct an approximate state that is a superposition of the sampled terms. And you can show that the number of terms, the number of samples you need in that approximate state is proportional to this, the one norm squared. Okay, so the stabilizer extent is an upper bound on the approximate stabilizer rank, but it is also directly related to the stabilizer fidelity. And I'll just remind you of the definition of the stabilizer fidelity. That is the maximum inner product with the stabilizer state squared. And there is a relationship between the extent and the fidelity, which is the following thing, and it goes through convex duality. So in particular, like you get to maximize over any kind of witness W of this quantity, the inner product squared with W inside divided by the fidelity of W. So if you plug in any witness state here, you get a lower bound on the stabilizer extent. But for magic states, things simplify, and one can show that the optimal witness is actually equal to the state itself. So for magic states, the extent is actually equal to 1 over the fidelity. Okay, so that's kind of nice. Right. So as I said before, like it's an open question to establish a good or exponential lower bound on the approximate stabilizer rank of magic states. So we asked a related question, can we understand the other measures of non-cliffness, the extent and the fidelity, and can we understand those things at least? And we asked specifically, can we understand how they behave under tensor product? Because if, for example, these quantities are multiplicative, then you just need to be able to compute them for 1-qubit states, and that's easy. And we were able to make progress on this question for the stabilizer fidelity and consequently also for the stabilizer extent. So I'm going to tell you a little bit about that. Right, so it's not hard to see that the stabilizer fidelity is not multiplicative. But I promise that there's still more to say here. So, why is it not multiplicative? So, if you have a Haar random n-qubit state, then you can show that the fidelity of psi tensor psi star, the complex conjugate, is strictly larger than the fidelity of psi times that of psi star with high probability. And how do you show that? It's like a 2-line proof. Well, first you show using like a union bound and properties of Haar random states that the fidelity of the stabilizer fidelity of psi and of psi star will be with high probability close to some polynomial divided by 2 to the n, close to like what you expect for the inner product of just one random state. But on the other hand, psi tensor psi star, if you take its overlap with an entangled state of those 2 registers that's like maximally entangled, then that overlap squared will also be 1 over 2 to the n. So this thing is bigger than that squared. Right? So that's how you can see that the stabilizer fidelity is not multiplicative for random n-qubit states. But then you can ask, well, is there a family of states where it is multiplicative, and is it an interesting family? And we are able to construct a set which is closed under taking complex conjugation, and for which, when you take any 2 members of the set, it's multiplicative. And this set, as you'll see, is somewhat interesting. Okay. So we call this set of states stabilizer aligned states. They don't seem to appear, as far as I know, anywhere else. I was told yesterday that in this new work, there's a generalization to mixed states, and I'd like to learn more about that from Roberto and Marco and Ryujin. Yeah, I think they haven't appeared for our work, and they have a kind of mysterious quality to them, so it would be good to learn more about their properties. So let me tell you what the definition is. Right, so we're going to define the set P sub k of stabilizer projectors of rank 2 to the k. And we say that a state is stabilizer aligned if it satisfies the following n+1 inequalities. Okay, so the maximum overlap between psi and the stabilizer projector of rank k has to be at most square root 2 to the k times the stabilizer fidelity for every k from 0 to n. Now, if I were to notice that because this is a projector of rank 2 to the k, and because it's diagonalized in a basis of stabilizer states, if I replace this square root with, well, if I remove the square root and just made this 1 over 2 to the k, this would just trivially hold, right? Because this is a sum of 2 to the k rank 1 projectors. So this, all of them are stabilizers, so this would always be less than the stabilizer fidelity if I had a 1 over 2 to the k instead of 1 over square root 2 to the k. So this strange square root is what makes this definition kind of interesting and non-trivial. Okay, so that's the definition of stabilizer aligned. Right, so what do we prove? So we prove that if you have two states that are stabilizer aligned, then the stabilizer fidelity is multiplicative. We also show that if your state is not stabilizer aligned, then psi tensor psi star has a larger stabilizer fidelity than the product of f of psi and f of psi star. And this one is kind of remarkable. The set of stabilizer aligned states is itself closed under tensor product. So, if I take two stabilizer aligned states and I take their tensor product, it's also stabilizer aligned. Now, right. So actually the proof of 1 and 3 is somewhat involved. And the, there's some kind of inequality that I mean, it's not hard to see that this inequality is enough to prove this 1 and 3. But to prove this inequality, we use the structure of entanglement in bipartite stabilizer projectors, which is, it follows from the classification of entanglement in tripartite stabilizer states, which was due to Bravi, Fattal, and Gottesman. Yeah, I mean, this proof is technically somewhat interesting, but relies on this kind of powerful theorem of Bravi, Fattal, and Gottesman. And to show part 2, so this is for 1 and 3, and then for part 2, there is a kind of explicit, again, in sort of an explicit entangled state you can put on this side, just like we did for the case of Harmonian states, show that there's a violation. Okay. So a useful corollary of this theorem is that if we have m stabilizer aligned states, then the fidelity of their tensor product is equal to the product of their fidelities. And so then you can say, well, are there actually any members of this family of states? Like, is this a useful definition other than that it has nice mathematical properties? Well, it's not hard to show that all single qubit states are stabilizer aligned. You just need to check this. There's only really one non-trivial inequality here, and the inequality is just that the stabilizer fidelity of a single qubit state is always at least 1 over root 2. So that's easy to check. And in fact, by similar arguments, you can show that 1, 2, and 3 qubit states are always stabilizer aligned. So what that means is, well, okay, we'll get to what it means, but we don't know. I mean, there's some n, which is the smallest n for which one can find states that are not stabilizer aligned. We don't know what that n is, but it's probably somewhere between 3 and where this Harl-Random argument kicks in. Okay, so we get from this multiplicativity of the stabilizer fidelity for pure 1, 2, and 3 qubit states. As we heard about yesterday, that's been extended to 1 qubit mixed states in this paper, Rupali, Takagi, and Tony Mikkel. And as a consequence of convex duality, we also get multiplicativity for the stabilizer extent for 1, 2, and 3 qubit states. And we proved that this is not always multiplicative if the for high dimensional states. But we didn't prove that for the extent, and we didn't know how to prove it for the extent, but it was later shown by Gross and Hamendal, Montealegre, Mora, and Valentin that the stabilizer extent is also not multiplicative in general. Okay, so because of these corollaries or theorems, we can compute these quantities, the extent and the fidelity exactly for magic states, and we have this kind of nice pleasing picture, which is, I mean, there's only one annoying thing, which is this inequality here. But so the approximate stabilizer rank is upper bounded by this pleasing function, cosine pi over 8 to the minus 2m, but that's actually equal to 1 over the stabilizer fidelity, and it's equal to the stabilizer extent. So that's kind of nice. And maybe you might conjecture that it can't be improved, and we don't have evidence for that aside from that it's nice, but it's a challenge to you to try to improve this further. On the other hand, the known upper bounds on the exact stabilizer rank that I would like to talk about next, they seem unlikely to be optimal, and I think there's probably quite a bit of room for improvement there. How much time do I have? 10 minutes, perfect. Okay, so now I was going to talk about the exact stabilizer rank and the upper bounds that we have and the best algorithm that comes from those. And this is going to be based on this paper, which is joined with Tom Kasim and Pekal Pashai. Right, so before our work, the upper bounds on exact stabilizer rank followed a similar strategy. First, you would take, some constant number of magic states, like 3 or 4 or 6, and upper bound the exact stabilizer rank of them using some extreme numerical search. And then you would use this sort of trivial submultiplicativity that if I want to decompose phi tensor psi, if I want to stabilize decomposition of the tensor product, I can use a stabilizer decomposition of phi and multiply it by a stabilizer decomposition of psi. So, then if I take my M magic states, I just divide them up into groups of C and I get a bound like this. This was the strategy. But step 1 is actually, even though, it just requires looking at constant number of magic states, is really not easy. And the reason it's not easy, and this is a table from Bravi, Smith, and Smillan, is because, if you look at this, this is the table that they got from using a heuristic algorithm for computing low-rank decompositions of n magic states. And they go up to 7 magic states. And they say that we believe these upper bounds are tight. But if you think about like this data point of 7 magic states, so how many, excuse me, 6 magic states, and the rank is 7. So the number of 6-qubit stabilizer states is like, was this 315 million? But now they're dealing with 7 tuples of 6-qubit magic states, or something, right? So the number of those is like 10 to the 48. So, and in fact, it turns out that this one isn't tight. And that follows from what I'll talk about, but it's really not easy to see how to do these numerics better, or what is the thing that will improve these bounds in a more clever way. So so this best bound from this this BSS paper is 6 magic states has a stabilizer rank upper bounded by 7. And then there was this work of Gosset from 2020, which showed in a mysterious way that the 12 qubit, 12 magic states has an upper bound of 47, which is slightly better than the 49 you would get from the submultiplicativity with this bound. And so what, then you get some upper bounds, you get 2 to the alpha m from Bravi, Smith, Smillan, alpha is 0.4679. From the Gosset paper, you get 0.4629. And in our work, we improve on these bounds using a different strategy. And it's only, it's still obviously not the ultimate thing that is going to bring us to the best bound. But it's, well, it is what it is, and I'm going to tell you what it is. Okay. So it involves considering, instead of, well, we're going to consider the magic cat state on m qubits. Okay, so what is that? It's a superposition of m magic states and the perpendicular state, m perpendicular magic states. A perp now is just, the single qubit states that's orthogonal to A. It's obtained from A by applying the Z Pauli operator. Okay, so this is a magic cat state. Every cat that I write in this part of the talk is going to be like in this magic basis. It's never like the normal cat state. Okay? And it's easy to see that the stabilizer rank of the magic cat state is always within a factor of 2 of the stabilizer rank of just m magic states. And the reason for that is, well, this upper bound, you can just take a stabilizer projector and act on m magic states and you get the magic cat. So and this thing doesn't increase stabilizer rank. That's easy. And on the other side, you can act with a projector onto 1-qubit magic state on the cat, and then you get back, your M magic states. And this 1-qubit projector can be written as a sum of two Cliffords, neither of which increase, so you can only increase by a factor of 2. Okay, so you get a factor of 2 between the cat and the M magic states. So what that means is that asymptotically, if we care about the asymptotic scaling with M, M magic, the cat state is just as good as M magic states. And but the reason that this cat state is sort of helpful is because stabilized decompositions of small magic cats are a little bit easier to find. And then it turns out that you can use them to build larger magic cats. I'll tell you about that later. So, if you look at the cat 1, that's a sort of uninteresting state. It's a stabilizer state. Cat 2 is also, it turns out, a stabilizer state. And the largest magic cat state for which we can exactly compute the stabilizer rank is the 6 qubit magic cat, and its stabilizer rank is 3. And we found decomposition by hand, and here it is. You can show that it's exactly 3 by establishing a low bound using some. I mean, this was more work than I think it should be. Like it would be really nice to have better ways of even proving a lower bound of 3 on, but in any case, we did show that. Okay, so then there's some low-hanging fruit, right? So if we have now this bound on cat 6, we know its stabilizer rank is 3, then we know that the magic states, 6 magic states has a stabilizer rank that's at most twice that. So we get this bound of 6. It falsifies the conjecture that the stabilizer rank of 6 magic states is 7, but it also improves the bound to 0.43 from like 0.46, whatever. Okay, but it turns out this is not the best thing to do with magic cats, and you can use magic cats in a different way to get an even stronger bound. How do you do that? Well, as I said before, the strategy is going to be to build big magic cats out of small ones, and then use the fact that a big magic cat has the same asymptotic stabilizer rank as M magic states. So how does that work? Suppose I have 2 m-qubit magic cat states written here. Then if I project them onto AA on like the last qubit of this one and the first qubit of that one, then I get, 2m minus 2 magic states. And if I project onto A perp, I get 2m minus 2 of the perpendicular magic states. So in other words, if I project onto cat 2, which is the sum of these two things, AA plus A perp, then I get another cat state, which has 2m minus 2 qubits. So in other words, I contract 2 m magic cats with a 2 magic cat, and I get a 2m minus 2 magic cat. So I've increased the number of qubits of my cat. And what's nice about this is cat 2 is a stabilizer state. So it doesn't increase the stabilizer rank. So what this says is that the stabilizer rank of 2 m-qubit magic cats is at most, the stabilizer rank of this is obviously from submultiplicativity at most chi of cat m squared. And so we get this inequality between the 2m minus 2 qubit cat state and that of cat m squared. So if we took 2 copies of cat 6 and contracted with cat 2, we could use this inequality, and you run through the math, and you get even better than what we had before. So then you can just try to keep going. And this strategy, the best strategy that we know is to contract many copies of cat 6 arranged in chain with cat 2s. These are all stabilizer. And then you get this inequality between a large cat with 4L minus 2 qubits and L copies of cat 6, which has stabilizer rank 3 to the L from submultiplicativity. And that gives us the best bound that we know, which is 2 to the alpha m, where alpha is roughly 0.3962. Okay. Right, so this is currently the best bound and leads to the best algorithm for exact simulation that we know for Clifford plus T circuits. And there is still a gap between this scaling and that of the approximate stabilizer rank, where the best bound, upper bound that I told you about has an alpha, which is roughly 0.228. And so there, now the state of the art in upper bounding the stabilizer rank and its relationship to classical simulation algorithms. But there's obviously a lot of questions. And many of the questions have to do with the fact that understanding, stabilizer decompositions is just extremely challenging, even if you're willing to do numerics. Like this question, can we find a non-trivial criterion? Someone gives you a state, like a state vector, 2 to the n amplitude explicitly. Can you certify somehow that its stabilizer rank is at least 4? Like, how do you do that? Questions like that are, they sound very simple, but we don't have any answers. Another question, which I think relates to, for example, Robert's talk, are there other simulation techniques that may outperform these ones as a function of the number of T gates? I mean, nobody has said this is the best classical simulation method. I mean, this method has a certain scaling with these mathematical quantities, and then that provides a reason to understand those quantities. But there may be other methods, like maybe this lambda polytope method or other ones that are just better. We haven't found them yet, so that's interesting to study. Is there in fact a gap between the asymptotic scaling of exact and approximate stabilizer rank? We don't know. Can we improve the lower bounds on these quantities? And I think improving the upper bounds on the exact stabilizer rank is fairly low-hanging fruit still, and challenge you to make progress on that. So thanks for your time.
Thanks, David. Questions?
So thank you for your interesting presentation. So I have a question on if these approaches of the stabilizer based simulation approaches can be also applied to like QDs with a general dimensions or even continuous variable systems where everything goes infinite, so but that might be a little bit hard.
Yeah, I don't see any reason why you can't. I'm actually not. Others might be more knowledgeable than I am about this. I wouldn't be surprised if someone has looked at this. I just I'm not aware of what the latest is for QDITs or for bosonic systems, things like that.
All right, thank you.
Other questions? Yeah, sure.
It's a bit vague, but I was curious. When you're talking about this L1 version of the stabilizer rank, what's the name again?
Stabilizer extent.
The extent.
Yeah.
Yeah. You remind me a little bit of this compressed sensing, right? Where you have a rank condition, you relax to L1 condition, then you can solve, right?
Yeah.
And then the question is there a simulation method that uses this extent directly instead of the rank?
Yeah, so I think you're talking about things like mirror descent and things like that.
So,
Right?
yeah, for example, yeah, or compressed sensing, right? Where they relax to the convex problem and then can solve it. But because it seems it's better behaved, right? This extent, right? So can you use that simulation directly? Or?
It is better behaved. I mean, our simulation method achieves the scaling that is like we know what the extent is of magic states, and our simulation method, it achieves linear scaling in that quantity. So asymptotically, I'm not sure if.
I see.
Yeah, I'm not sure if we can improve it by looking at this. I guess I'm not sure what we would.
But it achieves it because you can show that the rank equals to your position of the rank.
No. So the extent is an upper bound on the approximate stabilizer rank, but the best. So in other words, we have a stabilizer decomposition whose asymptotic scaling coincides with.
No, I understand that. My question is more: is there a simulation method that the scaling goes with the stabilizer extent?
Oh, I see. I see. Well, I guess
without knowing that they're the same.
Yeah, without knowing they're the same. That's a good question. It's similar to like in the robustness case, like robustness of magic was kind of like that, except that it works in the density matrix picture.
Mm-hmm.
And you seem to lose a little bit when you work instead of with pure states with density matrices. So the closest analog I can think of is the robustness of magic, but it's a good question. I don't know the answer.
I'm going to answer to you. There is algorithm extent. Yes,
Okay.
so basically it's based on Markov sampling, and then this extent is like the negativity, and yeah, that's and you don't need to use the rank. the stabilizer rank, you directly just use the stabilizer extent.
You get linear, makes sense.
Yeah, you get linear and extent, exactly. I can show you the paper later. Sorry, there's one more question here.
Thanks for awesome results. Just for simple questions, have you ever thought about that? Can we reduce the stabilizer rank for some lower phase magic states because T states induces a pi over 8 phase rotation, but maybe we can think about some pi over 12 or
Oh, yeah, so actually yes, so that what's interesting, or one of the things that we looked at when we studied this extent quantity is, does the extent give you the optimal stabilizer decomposition for states like what you're talking about, like cos theta 0 plus sine theta 1 or something like that, where theta varies, it's not just pi over 8. And what's interesting is that actually when theta is like a constant that's close to 0, then the extent is actually not the optimal approximate stabilizer decomposition. So you can do exponentially better for tensor products of those states using a decomposition in the standard basis, actually. So the extent is, it is interesting to look at those other states, and one of the things they've taught us is that the upper bound on approximate stabilizer rank that comes from extent is not always the optimal, it doesn't always give you the optimal stabilizer decomposition.
okay, thank you very much.
Any other questions? Here? Oh, what?
So my question might be related to the previous question, which is that now if you want to implement some gate, maybe not T gate, maybe you may not have a nice gadget, but you want to simulate it. Then it seems to me that it's natural to consider the decomposing the gate itself with respect to, say, the Clifford unitaries.
Oh, yeah.
Or something.
Yes.
Would that be just straightforward apply to that? What is there any like technical difficulty or thing?
Yeah, so in this paper with from 2018, you can get the Clifford plus T algorithm that I presented in the same way that you're presenting, and that's also how you go beyond this, T gate, and you can do other Z rotations or other non-Clifford gates using decomposing the gate into a sum of Clifford unitaries, and then using the one norm of the coefficients in those unitaries, and then sparsifying that using so that has been yes, you can get algorithms that way and go beyond Clifford plus T.
Right, thanks.
Right, I think we should go to the next speaker. Thank you very much, David.